Okay, so this is going to be part 2 of CCDs. Part 2. So this is just starting from the slide that I had made last time with some pictures of some CCDs. So we've got our CCD, the Pro line, and then we've got some of the professional CCDs that are in use in astronomy. Just a really quick recap of what we covered last week about CCDs. We talked about what they are, charge-coupled devices using the photoelectric effect to produce electrons when photons are incident on them. We talked a bit about the readout pattern, so I put a little reminder here. It's actually a different version. Oh, that goes over it. Interesting. So they get read out kind of row by row. So you can actually catch this happening while you watch between exposing and when it's ready again. That's the readout happening. They used to be very slow. That used to take minutes. Now it just takes a few seconds, which is a surprise to people like Paul and me, which is why it's interesting. Electronics got better and quicker. We also talked about the definition of quantum efficiency. So this was the basically the fraction of photons incident on the material that cause an electron to be produced. And we're going to talk more about quantum efficiency today in terms of the practicalities of how you'd actually measure it. And we went through how you calculate the plate scale and the pixel scale from the focal length of the telescope. So today we're going to move on and we're going to talk about sources of noise in CCDs. And that's gone all weird. It's all like multiple words. It's interesting. It doesn't look like that on my iPad. Okay, well, sorry about that. So what does a CCD do? Well, we already said, right? But we've got these like little buckets in the rows and the columns, and we're going to count electrons. These gets counted in a unit called an ADU, which is, I believe, analog digital unit. And that number, the ADU, that's the number that you see when you mouse over the image as you're taking it off the telescope. This is proportional to the number of electrons, NE for the number of electrons. And in fact, the number of electrons we say is equal to the gain of the CCD times the count, which is going to be in ADU units. So it's just a number. Okay, so there are complications. So in an ideal world, in an ideal setup, the count that comes off the CCD is just directly proportional to the number of electrons, the number of photons that are incident, right? Because we're saying that the number of electrons is equal to the quantum efficiency times the number of photons. So this is a quantum efficiency. So in an ideal world, the count that we measure is just proportional to the number of photons and you're done. But we don't live in an ideal world. There's sources of noise. And there's other complications. One complication is that, in my little bucket version here, if the electrons fill up the well, they can actually reach the full well capacity. And you can end up saturating the chip. So this would lead to saturation. So that if more photons fall on the chip, it doesn't record any further numbers. So if you do a very long exposure on something that's bright, you can hit this regime. Before you hit saturation, you can hit a regime where the response is no longer linear as well. And so that can add complications. And so when you're doing your observing, you want to stay in the linear regime. And so that's your ideal exposure time, is an exposure time that leaves you in this linear part of the CCD response. Okay, on top of these issues about like running out of space in your kind of electronic little buckets, there's various different types of noise. One source of noise, and you might not think about it of noises, but can be a variation in the quantum efficiency from pixel to pixel. So not every pixel is the same. That might be quite a small effect with modern electronics, but it's still a measurable effect as we can show. There are thermal electrons. This is why we cool the camera. right? Each of those wells produces electrons when a photon is incident on it, falls on it, but all materials make electrons with some probability. The hotter the material is, the more electrons are produced. So we cool the camera to minimize this as much as possible. But still, over time, the CCD will build up charge, will build up electrons, even if no light is falling on it. This is called the dark current. So noise in CCD, not every pixel is identical, and there are thermal electrons which create this thing called dark current. There's electron diffusion. So now looking like top down on our CCD chip, if this pixel gets really full of electrons, a few are going to get into the neighboring pixels. Electron diffusion. This can be particularly an issue if you're observing bright stars on a dark sky, right? Because you've got very bright pixels next to very dark pixels. And so professional astronomers talk a lot about this because this is a big source of noise that's hard to deal with. Then there's digitization noise. Digitization noise. You can only count in integers. So the ADU count will always be an integer. The gain is not always an integer. So there are some issues there. This is usually small. So we usually ignore this. I mean, these are actually all small, but this is usually really, really small. So we usually ignore this. And then there's the readout noise. So that process we talked about shifting the rows and then reading out each row. Each transition can introduce a very, very tiny error. They're very tiny in today's big CCDs. But the cumulative, like 4096 by 4096 steps that the most distant electron takes can actually introduce quite some noise. And we can measure this noise by just reading out the chip without exposing it at all. So we just basically say, everything should be 0, but let's read out the chip. And, calibration, what we're going to talk about today, is the process of kind of dealing with all of these little issues. So I'm actually going to start from the bottom. So here's the next slide. These are actually real bias frames from our CCD chip. So this is a 0-time exposure. So I said, there should be 0 everywhere, but these are integers, and actually they tend to be unsigned integers. It's something that means they're only positive. It used to be hard it used to take more computer memory, I think, to store negative numbers. And so in lots of code, you see these shifts that mean you never get negative. And so we do that in a CCD chip, in that the 0 point is actually not at 0. It's going to be at some number that we call the bias or the offset. So we call these 0-time exposures bias frames. They won't have 0 counts. They'll have some number of counts. And but as you see, they're kind of speckly, and that's the readout noise. So the speckliness in these pixel values is the readout noise. So putting that into kind of an equation, let's say the readout noise, which we'll call Rn, is the standard deviation of the counts in the bias frame. So this would be in those ADU units, in the count units. You could calculate the readout noise in electrons, so the amount of deviation in electron counts, if you knew what the gain was. So you'd do this gain times the standard deviation in the bias. So as we've discussed, FITS files are just arrays of numbers. That's how we'll interact with them later today. And so we literally just take the standard deviation of this array of numbers. And that will give us the readout noise. And then we take the average of it, and that gives us a lovely measure of this bias, which we're going to have to subtract from every further frame. And this is an example of actually 10 bias frames averaged together. So we get a nicer measurement of the bias. But obviously the standard deviation here is root 10 times smaller, because we've averaged 10 values. So the next thing that we want to deal with is the dark current. So remember, these were the thermally generated electrons. So these are two, again, this is real data from our CCD. This is some of the data I took this summer. And you can see that over time, the dark current just builds up, and it builds up in proportion to time. So increases linearly with time. I mean, with the caveat that if you actually, if you filled up every well with dark current, it would stop being linear with time, right? You would saturate, you get that same behavior. But these are very low numbers. These are hundreds of counts, which is incredibly low. This is a really nice CCD. Dark current is adventure time, very low, even at 13 degrees Celsius. So 13 degrees Celsius is not an impressive temperature to have your CCD at. That was the coolest I could get it the evening I took this data, because it was humid and it was the summer. And then I took it at 13 degrees, 18, I think, and 23. I think ambient was 23, to look at how it varied with temperature. So because these are thermal electrons, if it's warmer, you get more of them. And you can see here, it roughly is roughly linear increase with temperature as well, in this regime at least. But I'm not going to claim that it must be linear with temperature. I'm just going to say it increases with temperature. Honestly, this is so low that if the CCD is low, probably don't even need to worry about subtracting it. This is actually a fraction of the bias. So, but to do the most correct reduction, you would also subtract the appropriate dark current. Because it's so linear with time, you don't need to measure it for the length of your exposure. You can just measure it really well at one time and then scale it to the length of your exposure. So that's really nice. So you don't have to take a dark current frame for every frame you take, which would double the amount of time you take to take your data, right? You just take one really nicely measured dark current frame and use it for every science frame. But because it's a function of temperature, you need to take it at the same temperature that you're taking your data, the same CCD temperature. Don't really care about the ambient temperature. And flat fields, right? So flat fields are basically the way to deal with the fact that the pixels have a variety of quantum efficiency, and we also have variation in the optical path through the telescope and camera and stuff. So we're basically dealing with the variation in sensitivity, whatever its source is. Sensitivity. So our ideal flat field would be our little chip here being completely uniformly illuminated. So we have completely the same flux hitting every single pixel. So ideal would be a uniform illumination. We don't live in an ideal world, so we can't really do that, but we can get close to it. There are two, well, actually three, but there are two main ways that we can do this. You can use the twilight sky. You could use the daytime sky, I guess. It's just too bright. The daytime sky, you risk saturating the CCD. So use a twilight sky. So after the sun is set, as the sky is starting to dim, but before you see any stars. You don't want stars because you want uniform illumination, right? You want every pixel to be having the same light. So you want all the light basically to be coming from the blue sky. Or you can use a flat field screen. This is not ours. I forgot to take a picture of ours. You've all seen it inside the dome, right? There's a big flat screen. Now ours is not quite as big as this one, which is the flat field screen for the 6.5 meter MMT telescope, which I found on the internet. That's a very, very big telescope. But basically it's a white screen that we illuminate with bright lights. And hopefully it's roughly then constant illumination. Even unfocused, the telescope is only looking at a tiny bit of it.
So for space-based telescopes, are those like taken on Earth with the CCD before they're put in use, or do they?
That's a great question. No, you can actually have like a little internal flat field. So they have like I think they have like a little beam splitter, and they send it off to a little flat field that they illuminate. I should have had a picture of the SDSS flat fields. I'll find one later, but SDSS, it kind of shuts the dome slightly and illuminates the inside of the dome for the flat field. So there are sort of internal techniques that are used as well. And there's different reasons you'd pick different ones. Paul reminded me that the twilight sky is very blue. Whereas artificial lights tend to be much redder. Not so much these days with LEDs, but particularly when we were talking about filament lights, they were much redder. So, you know, if you're doing sensitive stuff in the red part of the spectrum, a dome flat might be the best choice. Whereas if you were doing blue imaging of some kind, you might really, really, really want your sky flat for the blue sensitivity. I mentioned there's a third way of doing this. So you can do something called a sky flat. And I think a few of us have been doing accidental sky flats. So this was the image that Shuei posted on Slack, wondering what was up. This is not quite a sky flat because you can see stars in it. There's dots of light, but most of the features in this are the features I expect you to see in a flat field. So features that we will note is that you have this outer attenuation, which we'll get to the source of. It's actually not to do with the chip so much as the optical path attenuation. I can't write. And then you get these, like this weird thing here. This is a speck of dust somewhere in the optical path. And it looks like a little donut because it's out of focus. Look just like the stars are out of focus. They look like little donuts. So if this, an actual real sky flat, what you do is you take lots of images at like random positions, and then you take a median, and it doesn't matter where the stars were because they get averaged out. We're not going to use that technique, but I just mention it. Another way to do it would be to take images while the sky is moving and the telescope is not, which a couple of people have kind of accidentally done. That's not quite good because you'll get streaks across your CCD sometimes, but yeah, we're not going to do sky flats, but just to mention you can do it. And I thought I should talk about why we have this outer dimming, and also point out that I did this too. This is my image of the Whirlpool galaxy, which I did without taking flats. And I can, because it's quite faint, galaxies are faint relative to the sky, I've had to adjust the contrast so much that you can actually see this outer ring of lower sensitivity, which I think makes quite a nice picture. So I don't mind too much, but if I really wanted to do a good job here, I would want to flatten that with a flat field. So what's going on? I found a GIF showing what's going on. This is not our CCD, but this is a camera with a shutter that's opening and closing. And if you look, this is our CCD, or one of them. You can kind of just about make out the petals. So the way the aperture opens and closes is in this sort of method. And as you can imagine, that means that the center of it gets more time being illuminated by photons than the outer parts of it. And so we have this variation of sensitivity. So the opening of the aperture reduces the sensitivity at the edge of the chip, just from the optical path. Okay, so here's an example I found online showing the process of fixing these problems. So this here, this one is the raw image. And you can see stars, but you can see a bunch of noise and some other effects. This is a CCD with quite a large dark current. So a lot of that noise is dominated by this dark current. Here is the flat field. So again, like we do, there's a lower sensitivity at the edge of the chip, and there's some of these dust specks making little donuts. You subtract the dark current and the bias, and you divide by the flat field to normalize the sensitivity, and you get your so-called science frame. And we do this in a way that propagates the errors properly and saves all the numbers so that we can make scientific measurements from the images. Yeah, and then just the last one, I thought this was just a nice little flow chart showing kind of the whole process. If it's useful, just in case it's useful. But so you start from your raw images. And in each case, so you have the row here that is the flat fields or your raw science images. You have to subtract the bias and darks and dark frames, scaled appropriately in the case of the dark frame. And then you have your dark subtracted images and dark subtracted flats. You average your flats together to make a best flat field measurement that you have. And then you divide your science image by the flats to get your calibrated images. Only at this point would you then do the alignment stuff, because all of this is all to do with the pixels. And so we do it in like pixel space before we then want to align things into sky space. All right, I want to tell you about a few other things you can do with the calibration data. We can measure the gain, which is pretty exciting. I like this. This is a really neat little thing. So we've got two flat fields that should have the same electron count in them, because they've got the same illumination and the same exposure time. And this one you have to do with dome. You have to do this with dome flats because you have to control the illumination. You can do it with twilight flats. The pixel to pixel variations between those two measurements should be dominated by electron counting noise. If they've got enough flux in them and stuff, they're not dominated by read noise or anything like that. And electron counting noise is just Poisson noise. So I don't know if you've done Poisson statistics before, but let me just tell you. If you have n events happening in the Poisson statistics, the standard deviation on that happening is the square root of n. So you count 9 electrons, the electron counting noise would be 3. So we have our two flat fields that should be identical. I guess I'll write this. They should be identical. So same filter, same exposure length, same conditions for taking them, same temperature, everything. Just take them one after the other. Let's say that F is the average flux in them. So we just take the average of the two. So this is the average count. And then we're going to say that sigma F is the standard deviation of the difference. So if you take flat field 1 minus flat field 2, it should be 0 because they should be identical, but it won't be 0 in every pixel. And the standard deviation of how much it differs from 0 is our measurement, is our sigma F. So this is the standard deviation. The electron noise, what shall I write that as? So let's say sigma E. Electron noise is then just the gain times that measurement that we've made. We've measured the noise in ADU units. So in electron units, the number of electron units is just the gain times that noise. But I already said that this is just Poisson counting noise. So the electron noise is also just the square root of the number of electrons. So on this side, we've got electron noise or electron count noise. And this is just number of electrons. Okay. But if we go up here back to the average count is just going to be the gain times the number of electrons. That's the definition of it. That's the other way around. It's the number of electrons divided by the gain. I'm sorry. Does that make sense? Yeah. Okay, so we can put that in here. So our electron noise is also equal to the square root of the gain times the average flux. Okay, so now we've got two equations for the same thing. So we can actually just combine them and solve for G. And hopefully I have enough room to write just at the bottom here. Then that means that the gain is equal to the average flux of the two flat fields divided by the standard deviation of the two flat fields. That's all stuff we can measure. So I did. So this is the flux, the average flux of two flat field frames. And then this is the standard deviation squared, because look, it's a square in the. And I've done it at a variety of exposure times so that, you could do it from just one measurement, but a more accurate measurement, we're doing it at a variety of exposure times, and then the gradient of the plot is your gain. That's kind of cool. I think that's just kind of neat that you can measure this from just two flat fields. Just a couple more things. We already talked about linear response. So this is the regime of counts where you have just directly that the number of electrons will be proportional to the number of photons. Or I haven't actually put the gain in here. So you actually have the counts. It's proportional to the number of photons. How do you do that? Well, one way to do it would be to look at a star with different exposure times and then count how many, count the flux of the star in counts and see how it varies with time. And this is the linear regime where the source counts just increase in proportional to time. Just more time, just more photons fall on it. I also mentioned saturation. So here's a couple pictures of saturation from professional observatories. They're not immune to it. Particularly, there are really bright stars on the sky. So if you're taking faint imaging, this happens. Basically, when things get saturated, the pixel count doesn't keep going up with the count of photons, and you get just weird features. You get both weird features in the center and overspill. So you get dispersion of electrons, making them kind of big blobs, cause all kinds of problems for doing faint imaging. So I measured this with Spiker earlier in the summer. And so here's the linear regime. And then as you keep doing longer and longer exposure times, and this is only in seconds, stars are bright. We hit saturation. It's starting to tend to no increase in counts.